Welcome second graders to the Dallas Independent School District STEM Environmental Education Center. And we'd like to welcome a number of schools today. First, we have students from Rolling Hills Elementary and Lancaster ISD. We have second graders from Martha Turner Riley Elementary in the Dallas Independent School District. We have students from Southwood Valley Elementary and College Station ISD. And all the rest are from Dallas ISD. And that is Young Elementary, Hotchkiss Elementary, and the Solar Preparatory School for Girls. Thank you so much for joining us today. We wish you could be here in person. I'm not sure that you would all fit in our center all at once, but virtually you do fit, so that works out quite well. If you are watching this and have not registered for today's field trip, you can still register. The way you register is by going to www.tiny.cc/EEC register. There you can get yourself or your class registered for this field trip, and we just use that information for our attendance purposes. Today's virtual field trip is going to be all about force and motion. So during this virtual field trip, students will discover that forces cause change. Students will also observe how magnets are used in everyday life and compare patterns of movements of objects. So we're going to start off today by exploring how forces cause change. That's going to be led by Mrs. Fuller. Next, we will discover that energy exists in many forms. That will be led by Ms. Nash. Third, we're going to see how we use magnets. That will be led by Mr. Monroe. And last but not least, we are going to observe patterns of movement with Mr. Ramirez. While we're doing all of that, you can ask us questions, and we hope you ask us questions. The way you do that is by going to www.tiny.cc/EEC-question-answer. Once you get there, you fill out a very short form and submit it to ask us any questions you have related to force and motion. You can ask us as many questions as you like, and we will do our best to answer all of them in the time that we have with you this morning. So let me stop sharing my screen here and turn it over to Mrs. Fuller, who is going to get us started with how force changes matter.
Hi, boys and girls. My name is Mrs. Fuller. This is my friend Lauren Chicken, and we're going to talk about how force changes matter. Or how force causes change. We've got three words that are real closely related. The first one is energy. Energy is the ability to do work. The second one is force. That's the thing we're focusing on today. Force is push and pull. Force can start things moving, can stop things from moving, can speed things up, can slow things down. And we even have a force called friction that acts as a slowing agent. So we're going to be talking about force and how it changes things. And our last word is motion. Motion is moving. So we're going to see a lot of things moving today. Well, you might say, well, Mrs. Fuller, why do you have a chicken when you're talking about force and motion? Well, she exhibited force causing change about 10 minutes ago because she laid this egg on my desk about 10 minutes ago. It's still warm. And she pushed the egg out of her body. So that was a push. That was a force. Well, how did she do that? She did that with energy. Well, where does she get her energy? She gets it from food, just like you get your energy from your food, except you don't eat worms. She eats worms. So we're going to put her down and let her eat these worms. She just flew off. All right. And let's look at some different ways that force can cause change. Now, one of the ways force causes change, let me move these pickles out of the way, is by direct contact. So let's do some direct contact demonstrations. This one's real simple. I'm going to put my hand directly on the little school bus. I'm going to push it toward you. I'm going to pull it toward me. Push and pull are forces. All right, so that's one. What about breaking things? I'm going to put some direct contact on a rock and break it. So if you've ever come out here to the Environmental Center, I know you've seen our fossil pavilion, and in the fossil pavilion are lots and lots of Eagle Ford shale rocks. We break them open with rock hammers and we reveal the fossils that are inside. So here's a rock hammer. I'm wearing safety glasses. So remember, safety first. That's true in every business. And here's a piece of Eagle Ford shale. You see what it looks like. We're going to tap it with the rock hammer and see if we can reveal a fossil. Well, I didn't see a fossil in that group. We got lucky this morning and saw one. So I'm going to try another one. How about that? All right, I think we hit pay dirt here. And I'm going to show you the fossil. We put force. Can you see that? Isn't that great? That is wonderful. All right. We put force on the Eagle Ford shale with the rock hammer, but the energy was supplied by my arm. And I got the energy from the food I eat, just like Lauren, the chicken, gets her energy to lay eggs from the food she eats. All right, so that was direct contact. Now let's do one about moving air. Okay, wind can supply the force for motion and cause change. So I'm going to blow, I'm going to use the moving air from my lungs to blow on this anemometer. This is a toy one, it's not a official one. Anemometers measure the speed of wind, and I'm going to blow on it. And it's going to go around in a circular motion. You know, it came to a stop. Friction is the force that caused it to slow down and come to a stop. All right. So let's look at something else. Have you ever wanted some limeade? Well, I like limeade, so I'm going to take a lime. Here's half of a lime. I'm going to put it in a juicer, and I'm going to pull the lever on the juicer, and it's going to force the juice from the lime into the glass. Can you see that? It's real hard, but I can do it. And there's the juice in the glass. And it changed the lime. The lime no longer has juice in it, and it's kind of flat now. So that was change due to force. Let's look at another one real quick. Oh, here's one. This is probably something you're doing right now. The pecans are falling. It's November in Texas, and everybody's looking for pecans on the ground. So I've got a couple of pecans here. We're going to put it and pull these two levers here, and we're going to, hear that? We're going to drop it on the floor. All right, I'll try another one. All right. There's the pecan right there. Change causes, the force causes change. All right, let's see. I've got another kind of nutcracker over here. It works in a similar fashion, but it's a little bit different. It has knife blades on here, and you just crack the sides off, the shell part, and it doesn't knock the pecan in half. Unfortunately, I don't think this pecan is any good. I think this is a bad one. Oh, well, there you go. That's what we got on that one. All right, here's another one. Here's a jar. I have to use this plastic thing to help me get a grip on it. We're going to make a circular motion with the force of my hand, direct contact, and we're going to open the jar. And this afternoon, I can have a pickle with my sandwich. I'll put the lid back on. Very good. Okay, so we've got another one here. I'm going to demonstrate push and pull. This one's pull. Yeah, here's a little ant. He's on a little string, and we're going to pull him toward you. And I'm going to change his direction, and I'm going to pull him toward me. Push and pull. Force is push and pull. All right, let's see if we've got another one. Here's another circular motion one. This is a top, and I'm going to push with my thumb and my forefinger against this little stick here at the top. Now, a little bit earlier, I kind of spin off into the universe, but there we go. and you can see it going around. It's not going to spin forever because friction is going to cause it to slow down and then stop. Another force that's very strong is magnetic force. And Mr. Monroe is going to spend his whole session teaching you about magnetic force and how it can start things, stop things, speed things up, slow things down, cause them to change direction. So we've got quite a few forces here on our earth, and they can help us do work. So remember, force causes change. And then the three words that we said were closely related to each other were energy. Energy is the ability to do work. Force is push and pull. And motion is moving. If you have any other questions about force causing change, Mr. Broughton will be glad to answer those. Thank you so much. Good day.
Thank you, Mrs. Fuller. Kieran from Seagoville Elementary saw Lauren and asked the question, why do chickens lay eggs? And it is not so that we can have breakfast. They lay eggs to reproduce, which means to have babies. And getting back to forces, though, once that chick is developed inside the egg, it will actually push its way out of that egg. It'll poke a little hole in the egg and then break its way completely out of that egg as it hatches. But it takes force to do that, a pushing force to get out of that egg for that little baby chick. And in order for that chick to do that, it has to have energy. So now we're going to learn about different forms of energy with Miss Nash.
Hello, welcome to my classroom. Yes, we're talking about energy. I hope you have a lot of energy today. It's a great day to go outside and use some of that energy playing, running around. So I've got a chart here, forms of energy or kinds of energy. Let's start with light. That's the most important one for all of us alive today, because it all starts with that light from the sun. Plants figured out that they could use that light energy to grow. They use the light energy from the sun, CO2 from the air, and water. And with those three things, they make their own food. They store it as chemicals in their leaves and their roots and their fruit. And then we animals can come along and eat that in turn. So somebody, I don't know who it was, ate a big bite out of the leaf of this plant. I don't think I'd like to eat this plant, but you never know. I'm gonna break that. I'm trying. Okay. So light energy. Also sound energy. Sound energy is energy we can hear. Sound is vibration. So vibrations move through the air, that's how we hear. They all sound vibrations move through water. Whales can hear in the ocean. They move through ground. Elephants can hear from long distance. But watch. You hear that sound? So the vibration, it's really loud there. Now if I go like that and then put my hand on it, I stop the vibration and the sound stops too. A fun thing to do is to explore a little bit volume and pitch. So volume means how loud or soft. Pitch means how high or low. So you can take a cardboard box of any kind and some rubber bands and stretch them around the box and then vary or change how tightly you pull them. So this one, I've stretched it really tightly across this part, and listen. This one is less tight. So you can see that one's vibrating faster than that one. Okay. And that again changes the pitch. So it's a fun thing to explore and make your own little guitar. Heat energy. We mammals make our own heat. We use that chemical energy from the food we eat, from those plants we eat, to make heat. And in the wintertime, we put jackets on to keep the heat in. Now, I've got a little toy here, and I can take my hands and rub them together, use friction to make them even hotter. Remember, Mr. Fuller talked about friction. Get them as hot as I can, and watch what happens. Put them around the bottom there, and look at that liquid going up, 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 up. And it's gonna, they call this a hand boiler. Now, water would boil at a much higher temperature. The liquid in here is bubbling there at a much lower temperature. But put it right down. So as it heats up, it needs more space, and that's why it moves around. But we heat. So the sun also, in addition to giving us light energy, also gives us heat energy. Now, we've also got chemical energy from the food we eat, all that yummy food we eat. We also got chemical energy that we can turn into heat. Like here, you hear that? It's almost gone. There's a little bit of liquid in here. This is a little can of isobutane propane fuel that we take backpacking. It's under pressure in this really tough little canister. But when I open it, can you hear that? A gas is coming out. I can light that gas, put my little food on top, and make my dinner. I can burn that. So it's not like the gasoline in your car. There's a liquid like that. It's burned in the motor to give us power. And we have electrical energy. So we're using it every day. We make it in different ways, but we're using it for lights, okay, in the classroom, in your home. We use it to charge up the computer and the phone. We use that in lots of ways. Then we have mechanical energy. That's what Mr. Fuller is showing you. Most of those will connect moving things. So there are two parts of that. There's potential and kinetic. So potential energy is just energy that's waiting to happen, ready, can go. And then kinetic is when it's actually moving. So let's do a few little demonstrations about that. Now, this again is a fun thing you can do at home. Make your own little ramp. Like Mrs. Fuller had one. I made these out of some cardboard. And I've got two balls here. One styrofoam, very, very light. The other is kind of a rubber ball, bouncy ball, kind of heavy. So we're going to have a race here down the ramp. Which one do you think is going to win? Now, they're both starting at the same height. What's going to pull them down the ramp? Gravity. But they have different rules, different mass, different weight. So let's see. Who do you think's going to win? Make the prediction. And the little bouncy ball is the clear winner. In fact, it rolls onto the floor. Now, we can change one thing here. We're going to change the height of the ramp. I'm going to put this up high. And we're going to do another test. Now, when we do these little experiments or tests, we need to change only one thing. So first I had two different kinds of balls on the same kind of ramp. Now I have two different ramps, or they're saying this one's higher, but I have the same ball. I just put a mark on this one so we can tell who's winning. Now, so this one's going to start up higher, this one down here. So make your prediction. Which one do you think is going to win? Let's see who wins. Here we go. 1, 2, 3, go. Okay, this one came down faster because this ramp was up higher. And so gravity was exerting a little bit more force on this side than here. So here's another little toy that we can look at the interaction between mass and gravity in terms of how much force is being exerted. So I pull this one to one side and let it go. And that force is transmitted all the way through and comes out the other side. Now, if I pull it up higher, what do you think is going to happen? Let's see. Okay, same thing. So more force. Now, if I take two, now I've got more mass. Let's see. So again, more mass, more force. And let's pull these two up together. And so a bit more gravity and more mass, more force. So this cradle, have a fun thing to play with. Now, I have a little assignment for you, or suggestion, something to do this afternoon or tomorrow. And I'd like you to think about different kinds of energy. So we've got light, sound, heat, chemical, electrical, mechanical, and we got nuclear, but we don't have a nuclear power plant in the classroom, so we're going to kind of ignore that. You probably won't see that outside or inside. Compare the kinds of energy you find inside with the kinds you find outside. So we think about going outside. If we could go outside today, go down to our lake, our pond, we might find our wonderful friend, the great blue heron at the lake. So if we were outside, let's see what kinds of energy we can find. The sun is going down. That's that light and that heat from the sun. You got the sailboats using that wind energy to move. We've got the fisherman. He probably has an electric or maybe a gasoline motor on his boat here. He might have a flashlight there. You got the birds flying, so they're using their muscles to fly. You got the plants growing using that solar energy to grow. The boats eat the plants, the fish eat the boats, and the great blue heron is waiting to eat the fish. So you can make a little chart or just take a piece of paper and make some notes. You can write words or you can draw pictures, and you can see what kinds of forms of energy you can find inside and what you can find outside. So enjoy yourselves and do a little bit of experimenting. Okay, make your own guitar, always a fun thing. And if you have any questions, Mr. Broughton will answer.
Thank you, Ms. Nash. The question that came in was, does the sun give us light for our classroom? And maybe if you have a window in your classroom and the shades are open, the sunlight could give you some light, but you probably also have lights in the ceiling, and those are powered with electricity. But if you did some research and you researched how we generate electricity, you could probably trace that back to the sun. So indirectly, yes, the sun does provide us the energy, even for the lights in our ceiling, if you trace the source of energy back far enough, because most of all of energy on Earth does come from the sun. All right, now let's move back into another kind of force, which is magnetism, and that's going to be led by Mr. Monroe.
Having a little difficulty here. We got it. Okay, good afternoon, students. My name is Mr. Monroe, and we're going to explore or investigate something that I used to think was magic, but I found out later on it was science, and that is magnetism. And that is the where a material has the ability to attract certain objects because of what their matter has in it, like iron, steel, and nickel. We're talking about magnets. And you know, I don't think you guys realize that magnets are all around us, and we kind of use magnets in our everyday lives every day. Now, to really get an understanding about how we use them, we have to learn how they work. And I'm sure you guys probably are familiar with the most common magnets that we have around us, or that you probably have in your classroom: a bar magnet, a horseshoe magnet, and maybe you just have a ring magnet around. And the thing that all these magnets have in common is the fact that each of these magnets, whether it's a bar magnet, horseshoe magnet, or a ring magnet, they have what we call poles, a north and a south pole. And it's usually located in the ends or the sides of those magnets. For example, this bar magnet, this end has an S, stands for South Pole. This end has an N for the North Pole. On a horseshoe magnet, there's an S for South Pole, N for North Pole, and a ring magnet, one side would be the North Pole, the other side would be the South Pole. Those strong attraction areas, they behave sometimes very different from the other ones. Now, the first time I saw a magnet being used, it was a huge magnet. And it was being used to separate certain types of metals that were going to be recycled. These metals had to be put in groups according to the way that they were aligned. And we know that magnets are attracted. And when we use the word attract, we're talking about a force of pulling toward. These magnets would attract metals that had iron, steel, and a little bit of nickel in them. And that way they could separate them from other types of metals. I have in this Petri dish several items. I have a rock, a piece of metal here, a penny, a thumbtack, some staples, a nail, a pop top from a soda can, a screw, and a ball bearing, and a paper clip that looks like this. And I'm going to grab one more item, another paper clip, and I'm going to use a small bar magnet, which to me, it's stronger than the bar magnet that I showed you. So it really doesn't make any difference about the size of the magnet. Some small magnets have a tremendous strength, or they have a tremendous magnetic field that surrounds them. So let's see what happens here. Oh, it's picking up some stuff. Wow. It picked up a lot of materials from the Petri dish, but it left some materials also. And that's how this huge magnet was working in a salvage yard. It would pick up those pieces of metal that had iron and steel makeup in their matter, and it would separate them. So that's one use that we have for magnets, to separate certain items or certain objects from other objects because of the matter that they're made out of. Now, what this magnet did not pick up was a rock, so there was no iron or steel in that rock. A piece of lead, which we know lead is lead. It doesn't have iron, doesn't have steel in it. It didn't pick up the paper clip because this paper clip is made out of plastic. It didn't pick up the pop top simply because the pop top came from a soda can, which is made out of aluminum. And it did not pick up the penny, which is made out of copper. You know, magnets have other uses also. They are used in the medical field. They're used in these very large machines that are used to take images of the human body so that they can find out if anything's going wrong internally or inside a human body. And those machines are called MRI machines. Also in your home, you know what? Your refrigerator has a magnetic strip, meaning a magnet that's in strip form that goes all the way around to seal your door. It's on the lining of your door of the refrigerator. So when you close that door, it seals that door so no warm air can come inside your refrigerator to spoil your food. Magnets are also used in phones, doorbells, and some of the toys that you guys might be playing with. It's also used in electrical power plants in the form of generators that help generate electricity or make electricity. They're also used in electric motors. And I've got a small electric motor right here that you wouldn't think that this was an electric motor, but it is. It's an electric motor that kind of like a pump that I took from my aquarium. And what it does, it has a blade that turns around, and that blade circulates water. It has a cover over it, but it circulates water, generating oxygen for the fish and the turtles that live in my tank, and Mr. Hoppy, the bullfrog. I'm going to flip the switch on and show you guys how this works. Now, it's run by electrical power, but I guarantee you the electrical power is not what's really doing that. I'm going to turn it off and we'll talk about that a little bit. This that you see right here at the end of this propeller is a magnet. It's very small. It's not a bar magnet. It's not a horseshoe magnet. It's not a ring magnet. But this magnet is using the attraction, being pulled, and it's also using another ability of magnets. You know, magnets have a north and south pole, and I know you guys have heard that before because our planet has a, what, north and south pole. But like poles of magnets, guess what happens? They repel each other. I've got two small bar magnets right here, and if I put the north poles toward each other, guess what happens? They won't attract. They repel each other. having a hard time pushing those together, making them fit. If I turn it around and use the South Pole against the North Pole, look what happens. So inside the motor, there is a mother magnet, and it's called an electromagnet, and it has a North and South Pole. And so once this magnet is in there, we're getting an action of repelling and attraction, which spins the propeller. So that's how an electric motor works, okay? Now, there is one other instrument that is used, and a lot of people use this little tool. They use it when they're afraid that they're in an area that they're maybe hiking or exploring and they don't want to get lost. They carry it with them. It's called a compass. And most people don't realize, because our planet has a North Pole and a South Pole, guess what? Our planet actually is the largest magnet in the world. Now, a lot of people like to refer to the North Pole as the magnetic north. And it does have a magnetic field with it. And so basically what happens is a compass uses that magnetic north because inside the compass, there is a needle. That needle is a magnet, and it is drawn to the magnetic north. So if you were lost and you looked at a compass and that little red needle was pointing that direction, that would be north. And I know that it's north because I'm in my lab, my classroom, and I know that that direction right there, that is north. Okay? And I guess it would be easier for me to show you. This is a model of a compass. North would be the indicator of in. E would stand for east. S would stand for south. And W would stand for west. Wow. You know, to help you understand that a little better, I have created what I call a homemade compass. And what I've done, I'm going to swing this around. I'm just going to start swinging wild. I'll settle it down. I have tied a bar magnet to a ruler, and I've suspended that bar magnet down where it's kind of free in the air, with the exception of the string holding it. And I'm going to settle it down just for a second here. And we're going to see if this will act like the magnetic needle inside of a compass. Now we remember I showed you north is that direction. Now it's trying to find its way. It's just about there. It's almost there. And it'll probably take it a little while. We've got a lot of interference. A lot of interference going on. Okay, it's just about there. So that is one very important use of a magnet, using its magnetic field to find or navigate to the north, magnetic north. Now, students, listen. When I was young, I often wondered who invented the magnet, because I thought it was magic at first. But then I found out it was science. And most things with science, somebody has discovered it or invented it. And I couldn't find anybody that had done that, any well-known person. Well, I found out something else when I was trying to find that out. I found out that magnets can occur naturally in our world. In fact, there's a story or a legend, and I don't have time to tell you that story, but it is said that it was discovered in a rock formation, a type of mineral called magnetite. And there are deposits of magnetite found all over the world, okay? The closest deposits that we have here in Texas would be in the state of Arkansas and Louisiana. And what I'm talking about deposits, I'm talking about rock deposits. There it goes. It's pointing to the north, guys. But listen, magnetite is just a rock formation, just like this. It's a natural magnet. It has a magnetic field to it, And you know what? If you were lost and you were trying to find your way and you're on top of a mountain that had a lot of these rocks, these magnetite, these lodestone rocks, guess what? Your compass would not work because it would be interfered with. It would be disrupted by the presence of the mineral magnetite or lodestone. Watch what happens when I get this lodestone close to the magnet. That would kind of mess that magnet, that compass up, wouldn't it? Yeah, sure would. Man, spin it back the other way. Look at it, it's following that lodestone. So you have seen and you've heard me talk about some of the uses of magnets in our everyday lives. They're very important to us, students. And besides, you know what? The planet Earth is the largest magnet in the world, although it is not the strongest. There is a magnet that is a hybrid magnet, probably man-made, that's only 3 feet long. It weighs about 6,000 pounds, and it is considered to be the strongest magnet in the world right now. They've even given it a name. They call it RD3, okay? Now, if any of you have any questions that you want to ask, I'm going to turn it back over to Mr. Broughton, and maybe he can answer those questions for you. I want you guys to have a good day the rest of the day and enjoy the rest of your virtual field trip with us. All right, Mr. Broughton.
Thank you, Mr. Monroe. The question that came in was, do animals use magnets? And yes, there are some species of birds that have a little bit of that natural magnet called magnetite in their brains, and that interacts with the earth that Mr. Monroe just told us was a giant magnet. And that helps the birds know which direction to fly when the seasons change. So they can fly south for the winter or north for the summer and adapt to the seasonal changes that happen every year. All right, now we are going to explore patterns of movement with Mr. Ramirez.
Hello, my name is Ms. Ramirez, and we're going to be looking at patterns of movement, including spinning, sliding, and rolling. So we're going to go ahead and start off with spinning first. So spinning is the motion that turns an object around and around. So we're going to look at some objects that are good at spinning. Now, first object is a common toy. It's a spinner top. So I'm going to see if I can get these to spin. And something cool, while I was experimenting with these and looking information up online, there is actually a world contest for spinning. So you can see I'm not the perfect person at spinning, but people actually submit, they create their own spinning tops. And the goal is to create a spinning top that will spin the longest. So that would be a cool little STEM challenge for you guys to see if you can make your own spinning top that will spin longer than your classmates. Another thing that spins is our planet Earth. And so you've probably seen a globe. So our planet Earth spins or rotates and along an imaginary line called an axis. So if we take a look at our globe here, it is spinning, it is rotating, and it is that spinning or rotation that causes day and night. So to help you guys remember the direction that the Earth spins or rotates, we're going to do a little brain break. You guys can stand. I'm going to go ahead and sit so I don't have to mess with my camera. But you guys can stand. You're going to take your right hand and put it on your left shoulder. And again, left, you just make an L with your hand. The hand that makes an L is your left hand. So right hand on your left shoulder, and you're going to spin in the direction that you're pushing. So I'm just going to spin in my rolly chair. And so this is a spinning motion. And again, the Earth spins or rotates in a counterclockwise direction. So that's how you can remember the direction the Earth spins. The next motion we're going to take a look at is rolling and also sliding. So sliding is when an object moves across a surface. So think about when you have a big heavy box and you slide it across the floor, or when you're on the playground and you're sliding down the slide. Then we also have rolling. So rolling is when an object turns over and over along a surface. So think about some things that might roll. When you're outside playing soccer and you kick that ball, it is rolling along the ground. So we're going to look at some examples of objects that are spinning and rolling. So I'm going to slide my box over this way. We have a couple of things here. We have some simple machines that we're also going to take a look at. We have an inclined plane here, so that's a type of simple machine. It's just a machine that is super simple and it makes doing work a lot easier. Y'all also know an inclined plane as a ramp. So I have a variety of different objects that we're gonna put on the ramp to see how they move. So the first object I have is it's called iron pyrite. It's called fool's gold as well. It's not real gold, but it sure does look like it. It's nice and pretty. So I'm gonna put it on the inclined plane. Do you think it's gonna roll or slide, and why? Also think about, as it's moving, what force is pulling it downward? So that's a thinking question. Now let's try our bouncy ball. Do you think it's gonna roll or slide? Also think about what force is pulling it down. Now let's take a look at our shark. Do you think it's gonna roll or slide? What force is pulling it down? And then our last one, take a look at our little guy on a shopping cart. Do you think it's gonna roll or slide? And then what force is pulling it down? So the force that's pulling it down, I hope you all said this, is gravity. So gravity is the force that pulls things down to earth. So if you want, you can take a moment to stand up, jump as high as you can. The force that's pulling you back down to the ground is gravity. It is pulling. Also think about what force stops things or slows things down. So why did this bear slow down and stop here at the ramp? Why didn't it keep on going? So the force that slows down motion is called friction. So friction is a force that resists motion and it slows things down. So think about when you're wearing socks and you're on a nice smooth floor and you run and slide across the floor. It is friction that is slowing you down. Now, what do you think is going to happen if I remove the slope of my inclined plane and I make it flat or horizontal? Do you think the bear is going to move? No, so why not? Also think about, what can I do to make it move? Well, I can apply a force, so I can push it. If I push it just a little bit, it moves just a little bit. If I do a big push, oops, it moves super far and it fell on the floor. So the amount of force that I exert also affects how far the object moves. So now we're going to take a look at some videos of how objects spin, or slide, and roll. So we're going to look at some animals in motion. So I'm going to share my screen with you guys. It might take just a second for the screen share to take into effect. Oh, I think my computer might have froze. There it goes. So I'm going to go ahead and present it full screen and see if it will cooperate with us today. So the first pattern of movement is sliding. So we have a red-eared slider turtle, and he is sliding off a rock. Other things that slide, think of when you play hockey, you are pushing the puck, you're applying a force, and that puck is sliding across the ice. Think about when you're on a slide at the playground. You are sliding down that slide and gravity is pulling you back down. The other pattern of movement is rolling. So here is a special toad called a pebble toad. They are from South America. And we also have a scary tarantula there. So our pebble toad is climbing a mountain. He is ascending, and so is that tarantula. What do you think is going to happen next? So that toad, he's working against the force of gravity. He's having to exert a lot of energy to go up the hill. All of a sudden, he falls, and you can see he's doing a rolling motion, just like a bouncy ball. So his ability of his body to take on that impact of falling and bouncing around is an adaptation that allows him to survive. So don't worry, he's totally fine. He has a very well adapted body for that motion, but that is the way that he can escape predators. And as he's going down the hill, he is descending or going down, and he's going in the same direction as gravity. So that's why he's able to go faster, and it also takes less energy to go downhill. The next animal movement that we have is spinning. So take a look at these hamsters on a little spinning wheel. Think about their motion. And when we describe motion, we can use words that describe speed. So speed tells us if something's going fast or slow. We can talk about direction. So if things are going up or down, left or right, or if they're going around and around. And then think about trajectory, the path that these hamsters are going. Are they going in a straight line? Are they going in a zigzag, or are they going in a circular path? So those are some words that we can use to describe motion as well. And then our next thing is a challenge for you guys. It's a little scavenger hunt. See if you can find two things that spin. So if you can remember spinning, you can do this hand motion here. See if you can find two things that slide. So if you have one hand like this and the other hand like this, and you slide your hand across like that, that's sliding motion. And then two things that roll. So think of things that roll. So see how many things you can find that spin, slide, or roll. And then think about, how can you make those things move faster? How can you make them move slower? And how can you change their direction? So I'm going to stop my screen share, and I just have one little last thing to show you guys, and it's an animal friend. Hopefully you remember that special turtle in that first slide, that red-eared slider. I have a real one right here. His name is Tortellini, and these guys are really good at sliding because they have a smooth shell on the underside of their belly. That shell is called a plastron, and it's so smooth that it allows it to slide easily off of rocks and logs. Now, what do you think would happen if these turtles had a bumpy, rough plastron? Do you think it would be able to slide as well? Why or why not? And then also think, we know gravity is helping to pull the turtle down under the water, but what's another force that's affecting the turtle as he's sliding off a rock or a log? So that's all I have for you guys today for motion of spinning, sliding, and rolling. We're going to go ahead and pass it back to Mr. Broughton. He's going to answer any questions.
Thank you, Mr. Ramirez. The question that came in was, why do animals move the way they do? Sometimes it's just for them to play and have fun, but other times they move a certain way to find food, or move a certain way to attract a mate, or move a certain way to avoid becoming prey to some other animal. That's kind of a short explanation of why they move the way they do. All right, now I'm going to share my screen so we can do a quick recap of what we did today. Today's field trip again was all about force and motion. During this virtual field trip, students discovered that forces cause change. Students also observed how magnets are used in everyday life and compared patterns of movement of objects. So we learned that forces do cause change, energy exists in many forms, we use magnets in everyday life, and objects and animals have patterns of movement. Thank you so much for joining us this afternoon. We appreciate you taking the time to learn about force and motion with us. We would like to know what you think about today's field trip, and you can let us know what you think by going to www.tiny.cc/EEC feedback and filling out a short feedback form about this virtual field trip. We hope to see you at the next field trip in about 3 weeks. Have a great rest of your day, and we'll see you next time. Goodbye.